let's jump into it. Ooh, I'm on the wrong slide. All right, so again, we're gonna just start with our challenge problem review from Monday, which again, this content is not on your exam. Your exam in 2 days' time on Friday is long answer on just chapter 11, which is your solution chapters. If you haven't regularly been attending SI and you're curious as to what sessions I've covered chapter 11, it was the first two SIs, so last week, as well as tonight we'll go over like a quick review. Okay, so number one, it looks like a multiple choice question, but it wasn't. It was just saying if you have a 0, first, second, and third order reaction, what would your units of K be? And I told you to assume that our time was in seconds, right? Because time could be seconds, minutes, hours, years, centuries. It can really be whatever. Okay, so A was for a 0 order reaction. An example rate law for this would be stated below, right? Rate equals K. And that's because 0 order reactions, the rate is actually independent of reactant concentration, right? So there is no concentration of reactant here because it'd be raised to the 0 power, right? And anything raised to the 0 power is 1. Okay, so knowing that rate always needs to be molar per time, where time here is seconds. So the units of rate needs to be molar per seconds, okay? And so in order for rate to be molar per second, our units for K have to be molar per second, or you can write it as molar times seconds to the negative first, okay? B, it was for a first order reaction. So I kind of wrote the rate law for first order reaction, right? So rate equals K times a reactant raised to the first power, right? So the units of concentration are molar. And so for units of K, you have to ask yourself, what times molar is going to give me molar per seconds, right? Which is the units of rate. And so K for a first order reaction should be 1 divided by seconds, or you can write it as seconds to the negative first. Okay. C, a second order reaction. Okay, so this is an example of a second order reaction. Rate equals K times concentration of A squared. Okay, and so again, rate needs to be molar per second. A, the concentration of A is squared, so the units associated with that would be molar squared. And so you're asking yourself, what times molar squared will give me molar per second? Okay, and so your units of K here should actually be 1 over molar times seconds, or you can write this as molar to the negative first times second to the negative first. Okay, same sort of thing with D, third order reaction, right? So an example of this would be rate equals K times the concentration of A cubed, right? So the units for A, concentration is molar. So because you cube it, it would be molar cubed. And so what units of K times molar cubed would give us the units for rate, which is molar per second. And so you'd find that the units of K here have to be 1 over molar squared times seconds. So all of that in the denominator, or you can write it as molar to the negative first times second to the negative first. Okay, and I know some of these challenge problems may seem, a little intuitive, a little bit simple compared to a lot of the challenge problems you've seen in the past. And that's really because this chapter, we've laid the foundations for it. And now next week, we'll kind of build off these foundations. Okay, so these problems may not have seemed like the best, may not have really seemed to challenge your knowledge, but these concepts and skills will be applied to harder problems. Okay, so it is important. So 2 asks, what is the reaction order or the overall reaction order based on the rate law? Okay, so rate equals K, our constant, times, reactant A, reactant B, reactant C, and reactant D. Okay, so remember the order of each individual reactant is its superscript. Okay, so A, whatever that reactant is third order, right? Because that's its superscript. B, reactant B, is 0 order. Okay, reactant C is second order, reactant D is first order. So to find our overall reaction order, all you do is add up those superscripts, right? So 3 plus 0 plus 2 plus 1, your answer should have been 6C. right? And I may have left K off on the original problem. And if I did, I apologize. I did not mean to. Okay, really, I just wanted you guys to add the exponents. Problem 3, again, very similar. Here they ask for the order of each individual reactant and the overall order. Okay, so again, the order of each individual reactant is its superscript. So nitrogen monoxide is second order, right? So that should eliminate option B. And diatomic oxygen is third order, eliminating A and B. Okay, and so then lastly, it's just what's the overall order? You'd add 2 plus 3. The overall order is 5. So the answer to this one should have been C. Okay, again, this will be important. Okay, and this is a very simplified version. We did one as an example on Monday together. A problem like this where you have a rate law and some of your components are doubled, maybe some are halved. The example we did on Monday, I think reactant C was increased by a 6-fold, something like that. This type of problem is very common where you're given the rate law, you're told how the concentration of a couple reactants change and what happens to the rate. Okay, so here it's a second order reaction. A is doubled. Okay, so basically it would be times 2 squared. 2 squared is 4. Right, so I'll show that on the next slide. Right, rate equals K times the concentration of A squared. Right, so let's just say the concentration is A. We'd find that the rate equals K times A squared. Now, when we double the concentration, right, we'd call the concentration 2A, right, which is the actual question here. And when you solve for the rate here, rate equals K times 4A squared. So as you can see, there's a 4 here that isn't on the other side. That's how you know it's 4 times as fast. So it would quadruple. Okay, this is a very simplified example. The one that we did together, or that I kind of had you try on your own on Monday, was much harder than you'd see on the exam. Okay, so if you haven't seen the example one on Monday, where I believe the rate increased by 9 times the initial rate, if you can do that problem, any of these that they throw at you should be pretty simple. Okay. Problem 5, you're given just a general formula. Again, we haven't really we're just using letters to represent reactants and products. You're told the initial number of moles of C and the volume of solution. And then you're told after a certain number of seconds, this is how much of C you have left. And then based on this, what's the rate of formation of E, F, and what's the rate of disappearance for A? Okay, and so, right, this problem they're asking about E, F, and A, but they give you information about C. Okay, so whenever they give you information about some reactant or product, and then they ask for the rate of a different reactant or product, you're going to use your relative rate formulas. Okay. So I started out just by writing my formula that was given, and then they gave us moles of C, right? But when we talk about rates, the numerator is changed in concentration, okay? And so I'm going to convert from moles of C to my concentration of C by dividing by my volume. Okay, so my initial condition, I'm at 0 minutes, right? No time has elapsed. And my concentration is 13.7 moles of C divided by my volume of solution. And I find that my concentration of C initially is 5.33 molar. Now I do it for the final after kind of like my final time stamp, right? So the time for that is 240 seconds, which eventually I ask for it in terms of molar per minute, my rate. And so 240 seconds is 4 minutes, right? And what's my final concentration? Well, I'm told that I have 5.88 moles of C remaining. Divide that by the volume to find that my final concentration of C is 2.29 molar. So what's my rate of C? Which rate of C is, again, change in concentration of C per change in time. And I just input it, right? I do my final concentration, 2.29 molar, minus my initial concentration, 5.33, and I divide it by 4 minutes, because again, I eventually ask for these rates in terms of molar per minute. Okay, that's why I converted it to minutes and didn't leave it as seconds. What I find is that my rate of C is negative 0.76 molar per minute. And the fact that it's negative makes sense because C is a reactant, meaning it's going to be disappearing as time goes on. Okay. Now, I wasn't asked about the rate of C, though. I was asked about E, F, and A. Okay, and so in order to find the rate of E, F, and A, I have to use my relative rates, right? And so to do relative rates, you're going to do 1 over the coefficient of whatever compound this is. So 1 over the coefficient for compound C multiplied by the rate of C, which is change in concentration per change in time, equals 1 over my coefficient for whatever compound E is times its change in concentration per unit time, which is really just rate of E. Okay? Now you might notice that I put a negative sign in front of 1 over C, and I put a positive sign in front of 1 over E. Okay? Put a negative sign in front of it if it's a reactant, right? That's just acknowledging that it's going to be disappearing. And put a positive sign in front of it if it's a product, right? So C is a reactant, E is a product, and so that's why I have those respective signs there. Okay, and so my coefficient for C is 2, based on my balanced chemical equation. So negative 1 over 2 times my rate of C, which I solved for above is negative 0.76 molar per minute, is equal to positive 1 over the coefficient in front of E, which is 4, times its rate of appearance, right? Because it's form or rate of formation. And so the rate of E, which is just equal to the change in concentration per unit time, is equal to 1.52 molar per minute. Okay, it's basically twice as fast as C, and it should be positive because it's a product. Okay, so I'm going to do the same exact things for F and A, right? So again, 1 over my coefficient in front of C, which was 2, and I'm going to put the negative sign here because it was a reactant, multiplied by my rate of C is equal to positive, because F is a product, 1 over the coefficient of F. So in the balance equation, the coefficient was 3 times the rate of F. Okay, and when I solve for it, I find that the rate of F, it would form at 1.14 molar per minute. Okay, lastly, I do the same thing for compound A, right? So I'm sure, and again, negative sign, 1 over the coefficient of C times the rate of disappearance of C is equal to 1 over the coefficient of A, which the coefficient of A was 1 here, so it's 1 over 1. Realize that I have the negative sign here because A is a reactant, so it's going to be disappearing, and I can solve for the rate of A, and it comes out to 0.38, and that would again be molar per minute if I included the units. Okay, before I go on to this last problem, were there any questions with those first 5? Okay, and while maybe people are typing, or maybe unmuting their microphone, there were 2 little things on this problem that I didn't mean for it to seem tricky or to trip you guys up. I wrote 0.35 moles and 0.15 moles down here. If I didn't give you a volume, you can't solve for that, right? It has to be a concentration. So those were supposed to say molar. I apologize. And then in this table, I think it said S2O8. It was supposed to be this reactant S2O32 minus. Again, if that deterred you from doing this problem, I apologize. That was not my intention. But this is a great problem and something that you will definitely be expected to do on the exam, both multiple choice and long answer, when you get to the exams on chapter 12. Okay, this won't appear on Friday's exam as a reminder, but when you get to getting tested on chapter 12, this is definitely, every part of this is something you have to do. Okay, and so basically they want you to find the rate law and the value in units of K, which you're going to use this table to do. And then they want you, based on your rate law, to solve for the overall order and the rate when you have a certain concentration of your reactants. Okay, so remember that when you're trying to solve for reaction order, right, it's important to pick experiments where the concentration of one reactant changes, but the other doesn't. Okay, so to find the reaction order of S2O3, I'm going to use experiments 1 and 2, which I correlate to these first two columns. Because as you can see, S2O3 doubles in concentration, while iodine does not change in concentration at all. Okay, and this is the general setup you're going to do. Okay, now I put the data from experiment 2, or that second column, for both concentration and rate in the numerator. If you wanted to put the data from experiment 1 in the numerator, that's fine. You just have to stay consistent from one side of the expression to the other, or one side of the equation to the other. Okay, so I personally put experiment 2 data in the numerator because when I do this quotient of my concentrations, I like it to always come out as a whole number, or not a whole number, but I like it to be greater than 1 if I can. Okay, so I'm just going to plug in my concentrations from experiment 2 and experiment 1. So S2O3 was 0.2 molar in experiment 2 and 0.1 molar in experiment 1. And that ratio raised to the n power, which is the order for this reactant, is going to be equal to the ratio of our rate in experiment 2 divided by our rate from experiment 1. Okay, and when you do this division out, you basically find that 2n equals 4, basically saying that as the concentration of S2O3 doubles, the rate quadruples. Okay, and so you can use your log rules or kind of just plug in numbers for n and find that n is 2, meaning S2O3 as a reactant is second order. Okay, now that we know that, our next step is to do the same exact thing for iodine. Okay, and so again, be careful to pick experiments where only the concentration of iodine changes, or you will be led askew. And so I put experiment 3 data in the numerator, experiment 2 data in the denominator. And so I basically found that 2 raised to the m equals 8. Basically meaning that as our concentration of iodine doubles, our reaction rate increases by 8 times. Okay, and when we solve for m, we find that it equals 3, meaning that iodine is third order. Okay, so what's our rate law? Or our basic rate law right now is rate equals K, which we still need to find, times the concentration of S2O3 raised to the second, because that reactant is second order, times the concentration of iodine cubed, because iodine is third order. Okay, to solve for K, what you're going to do is you're going to plug in data from one of the experiments. Okay, you could have chosen 1, 2, 3, or 4. Okay, personally, I tend to choose experiment 1 most times, typically because my concentrations are the most simple number. But again, you should get the same answer no matter what experiment data you plug in. And so when I solve for K, I eventually find that K equals 6.47, and the units of that are 1 over molar to the 4th times minutes. Okay, you could also write the units as molar to the -4th times minutes to the -1st. Okay, and so my absolute complete rate law, I write directly below that. Okay, so my complete rate law is rate equals 6.47 molar to the -4th times minutes to the -1st times the concentration of S2O3 squared times the concentration of iodine cubed. Okay, so that was one portion of the question. The next portion was, what is the overall reaction order? Well, that's just when you find that just by adding our superscripts. So 2 plus 3 is 5. Our reaction order is 5. And then the last part of this problem, it asks for the rate when there's a specific concentration of each of these reactants. And so all I did to find the rate is I just plug in 0.35 molar for my concentration of S2O3 and plug in the concentration of 0.15 for iodine. And again, I use my value of K to solve for the rate. Okay, are there questions on any of those problems before moving on? And if there aren't questions, if people want to sign in right now using your NetID in the chat, that'd be greatly appreciated. Okay. So quickly looked, and I don't think anyone's put in a question. If I miss your question when it's up in the sign-ins, again, feel free if you can, unmute yourself and just ask. Okay, so this is a general chapter overview. I actually left it from one of the sessions. I didn't mean to leave next session in there. We're gonna kind of quickly, there's probably about 5 or 6 review slides. Again, if you want a more in-depth review, definitely go back to just last Monday or last Wednesday session, where I go through these a little more slowly. Again, this is just to hit on the main points and kind of jog your memory and hopefully give you the opportunity to ask questions on any of this. Okay, so kind of our first portion is solution composition. And remember that every solution has 2 components. Okay, there's the solute, which is the portion that gets dissolved. It's almost always in the lesser amount, right? So there's almost always way more solvent than solute. And more often than not, it's a solid, okay? It can be a gas, liquid, or solid, but for our purposes, it's typically a solid, okay? But definitely for your multiple choice exam, remember that a solute can really be in any phase, okay? Solvent is typically it's the portion that does the dissolving, okay? So it's typically in large amounts. And in this course, our solvent is 99% of the time a liquid, okay? And probably 80% of the time it's water, okay? Again, a solvent can be in any state, liquid, gas, solid, but again, in this course, it's almost always a liquid, okay? And so this relationship is really important, right? Because sometimes we're trying to find mass of a solution. So the mass of the solution is equal to the mass of the solute, or solutes if there's multiple, plus the mass of our solvent. Same with mole fraction. Remember, mole fractions always add up to 1. Okay, so when you add up the mole fraction of your solute or solutes and the mole fraction of your solvent, should add up to 1. Same with mass percent, right? The mass percent of your solute and solvent should add up to 100%, because again, these are your 2 components of your solution. Solution composition, right? So these are our measures of concentration. So molarity, we're pretty used to, it's moles of solute per liter solution. Molality, right? The numerator is the same, moles of solute. The denominator, however, is different. It's kilograms of solvent. Okay, so definitely note that. Mole fraction, it's moles of whatever component you want divided by total moles. Mass percent, again, mass of a specific component divided by the total mass. Then you multiply it by 100 to turn it from a decimal to a percentage. And lastly, normality. I just want to touch upon it briefly because this was one of the questions somebody posed. I don't remember if it was last Wednesday or Monday, whatever I did that activity. Normality is basically the same thing as molarity. Okay, so I really don't expect normality to show up on the exam on Friday. I really don't. Okay, but realize normality is basically the same thing as molarity. The difference is actually the numerator. Instead of moles of solute, it is moles of what I'm just calling the important portion. Okay, and the best example of where you see normality is in acids. Okay, and the reason for this is when you're dealing with acids, you don't actually care about the entire acid. The only portion you care about is how much H plus you have. Okay, and so sulfuric acid is an example where you'll see normality a fair amount, right? Because if you have a 0.1 molar sulfuric acid solution, your concentration of H plus, that portion you care about, is actually 0.2 molar, right? Because there's 2 hydrogens per 1 molecule of sulfuric acid, okay? And so for an acid like sulfuric acid, instead of labeling a bottle 0.1 molar sulfuric acid, it would probably be labeled as 0.2 normal or normality sulfuric acid solution. Really what that's telling us is that the concentration of H plus, the important part, is 0.2 molar. Okay? And so hopefully that kind of answered your question about I got a couple questions about normality. So hopefully that clears it up a little bit. But again, if you ever see it on the exam, treat it very similar to molarity, right? So if they say that you have a 0.2 normal solution of some acid, just drop the acid and say I have 0.2 molar H plus, okay? Now, as you'll see from the challenge problems later tonight, and I'm sure on your exam Friday, you have to be very comfortable interconverting between these measures of concentration. You should be able to start with any of these 4 units of concentration and be able to convert to the other 3 with no issues. Okay, that's very important. Okay, and whenever you're given one of these units of concentration, you actually can start with any amount, right? You have to make an assumption. Maybe you'll say, I have 1 liter of solution or 50 billion liters of solution, right? How much you actually assume shouldn't affect your end answer, right? But if you're given these units of concentration, these assumptions will make your calculations to interconvert easiest, right? So if you're given molarity and you're trying to convert to any of the other 3 units of concentration, if you make the assumption you have 1 liter of solution, that will make your life easiest trying to convert to any of the other units of concentration, right? Mass percent, it's easiest if you assume you have 100 grams of compound or solution, depends on what you're talking about, right? In this chapter, we'll be talking about solutions, but we saw mass percent in chapter 4 in relation to compounds when finding empirical formulas. Okay, mole fraction, if you assume you have 1 total mole, that will make your calculations the easiest. And molality, assuming you have 1 kilogram of solvent. Basically, you're making assumptions that make your denominator the easiest to work with. Okay? And again, just to reemphasize, if you don't want to use these assumptions and you want to use a different number, that's okay. At the end, you will still get the same answer, right? If you're converting from molarity to molality, whether you assume 1 liter or 55.384 liters of solution, you will actually come out to the same molality, okay? But again, these assumptions make it easiest. Okay, moving on, this is kind of like your one-stop shop for factors that affect solubility. You know, this probably won't be hugely important for this exam on Friday. I'd be very familiar with Henry's law, but right, this is more theoretical questions. This is more likely to come up on the multiple choice. Not saying it can't come up on your long answer, but it's a little bit harder for it to. Okay, so there's 3 main factors that affect solubility. The first one is kind of the quality, not the quality, that's the characteristics of the compound, right? And we use this phrase, like dissolves like, right? So if we have a polar solvent, that will dissolve polar molecules, which molecules are made up of non-metals. So polar molecules would be a molecule like water, or really just anything that has polarity. And ionic compounds as well, right? So if you ever see a metal and non-metal together, you should automatically know that that's going to dissolve really well in polar solvents like water, okay? Non-polar solvents are better at dissolving non-polar molecules, right? So a great example of a non-polar molecule is really any hydrocarbon chain, which is just carbon and hydrogens. There's no polar bonds. It's a non-polar molecule. It'll be dissolved in non-polar solvents. Okay, so this brings up kind of the end of 1127, right? It's very important to be able to look at kind of the formula for a compound, be able to draw the Lewis structure, and then ask yourself, is this molecule polar or not? Okay, they expect you to be able to expand on the knowledge from last semester, to draw those Lewis structures, identify what molecules are polar or non-polar, and then from that, be able to decide, would it dissolve in a polar or non-polar solvent? Okay, and a great example of that was the first challenge problem from last Monday, the first SI of the semester. I believe that example was, what solvent would methane best dissolve in? Okay. A second factor that affects solubility is pressure, right? So as pressure increases, solubility will increase. And we can see that in Henry's law. And so Henry's law says C, which is the concentration of dissolved gas, is equal to K, which is some constant that you would solve for or be given, times P, which is the partial pressure of the gas above the liquid. Okay, so as you can see from the equation, pressure and concentration are directly proportional. If one increases, the other will increase. If one decreases, the other will decrease. Okay, so Henry's law is very, very important. Okay, and lastly, temperature. Temperature, this has some exceptions to it, definitely, but I have listed the general rule of thumb. Okay, so as temperature increases, the solubility of solids typically increases. As temperature increases, the solubility of gases typically decreases. Okay, there's definitely exceptions to both of those rules, but as long as you know those general trends, that should square away if it shows up on like a multiple choice question. Okay. So now let's jump into our colligative properties, which is the main portion of this chapter, and especially the main portion on open-ended exam, because we have 4 big colligative properties to look at. So before we jump into those, what is a colligative property? Okay, so these are properties that are affected by the amount of solute present, but not the identity, right? It doesn't care if it has a positive charge or a negative charge. It wants to know how many molecules or ions are floating around in this solvent, okay? And so we have 4 different colligative properties we're going to look at. The first is vapor pressure, which we see in vapor pressure lowering, okay? And we can express this mathematically using Raoult's law, which states the pressure of gas above our solution is equal to the mole fraction of our solvent times the pressure of our pure solvent, the vapor pressure of our pure solvent. Okay, so as you add more and more solute, the mole fraction of your solvent is going to decrease, causing the vapor pressure of your solution to be lower, right? Vapor pressure lowering. That's why we call it that. And really the only things I want to highlight here is I would really emphasize that this is mole fraction of our solvent, right? So often we talk about our solute, you know, up until this point, we don't really care much about our solvent. And so I'd really highlight that this is one of the times that we actually really care about how much solvent there is. Okay, so please make sure you know this is mole fraction of our solvent, not our solute. And then in case you kind of face any theoretical questions about this down the road, you might be asked, why does the vapor pressure lower? And basically what happens is the solute particles are blocking the solvent particles from going from the liquid portion up to the vapor gas phase, right? Kind of just knowing that these solute particles block the solvent particles is kind of enough. Okay, that's why we see the decrease in vapor pressure. Okay, our second colligative property is boiling point elevation, right? So remember that compared to a pure solvent, our solution is going to have a higher or increased boiling point. Okay, and the expression for that is shown below. So its change in boiling point is equal to Kb, which is going to be some constant, and it depends on the solvent being used. So you'll be given that on the exam, or again, you'll be solving for it. It's definitely not something you need to memorize. And it's Kb times small m, our molality. Okay, so definitely make sure you know it's the molality times I, our Van't Hoff factor. Okay, and Van't Hoff factor is basically just accounting for if molecules split into ions when they're added to solution, right? So compounds like glucose don't ionize, right? It's covalently linked, and when you dissolve it, it'll be dissolved in the water, but it's all still one molecule. However, when we add NaCl into water, it's going to split into 2 different ions, Na plus and Cl minus. And so that's what the Van't Hoff factor accounts for. Okay. Our third colligative property is freezing point depression. I really don't have much to say about this. It's exactly the same as boiling point elevation. Just kind of realize that they move towards the extremes, right? So boiling point, we think hot. And so when it becomes an impure solvent, right? So you're making a solution by adding solute, the boiling point is going to go up towards the extreme, while freezing point, when we add a solute to a solvent, the freezing point is going to decrease, again, moving towards the extreme of colder. And that's, again, why we call it freezing point depression. Okay, so that's really all I want to say about that. And then lastly, we have osmotic pressure. Okay, and osmotic pressure is the pressure required to stop the process of osmosis, which osmosis is the net movement of water from areas of low solute concentration to high solute concentration. Okay, so typically, if you have two chambers, one has pure solvent, the other one's a solution, your solvent's going to flow from the pure solvent side through a semi-permeable membrane to the solution side. Okay, and a semi-permeable membrane is just a layer that allows for the passage of solvent, but not solute particles. Okay, the equation is listed as it is, so that pi stands for osmotic pressure, which we measure in atmospheres. I would definitely note that this equation, M is molarity, right? It's not molality like our freezing and boiling point, but again, rather it's molarity, which is in moles per liter. R is our ideal gas law constant, 0.08206, and our temperatures in Kelvin. And again, this equation also has I, that Van't Hoff factor. Okay, so kind of the last note I would have is that out of our four colligative properties, I, that Van't Hoff factor, it doesn't show up in Raoult's law, the vapor pressure equation, right? But it shows up in our boiling point, our freezing point, and our osmotic pressure. Okay, and the next slide was just to get us thinking about osmotic pressure a bit, because another thing that a couple students brought up to me is that they didn't quite understand osmotic pressure, and maybe they don't really get the fact that there is pressure behind this running of water. And so I'm going to kind of compare it to a river, right? So kind of imagine, I'm imagining a river up in New Hampshire that kind of goes down. It's the Swift River, the mountains, and during the summer you can actually jump in it, and it kind of takes you kind of like a water slide down the rocks. It's really, really fun. Okay, but the rivers, right? Rivers naturally run downhill, right? Gravity is its driving force. Okay, and so if you jump in that river, it's going to push you down, right? It's exerting some amount of force or pressure onto you. Okay, and we can measure this, right? You could measure the force or pressure, or maybe you'd measure the speed of rushing water if it's a river. Okay, so let's kind of use that as an analogy for osmotic pressure. Well, in osmosis, like in a osmotic pressure environment, right, water is rushing down its natural gradient. So instead of it going downhill with gravity, the natural gradient for osmosis is from areas of low solute concentration to areas of higher solute concentrations. Okay, and so this rushing or this flow of water creates some amount of force or pressure. And so it's that pressure or force that we're measuring, and that's what our osmotic pressure is. Okay, so hopefully that made it make a little more sense. And I think this is the last slide, just some random notes. So in terms of vapor pressure stuff, remember our two terms, non-volatile and volatile. Okay, so whenever a non-volatile solute or compound is added, right, it will not exert a vapor pressure, right? Its only effect on our vapor pressure is that it'll cause a lowering of the vapor pressure, but only because it's going to affect our mole fraction. Okay, and so non-volatile solutes or compounds kind of indirectly, well, they don't indirectly, but they affect our vapor pressure only in the fact that they affect our mole fraction of our solvent. Okay, and so for here, you just use your normal Raoult's law. But what happens if we have volatile solutes - compounds? Okay, well, if something's volatile, it means they exert their own vapor pressure. Okay, and so if you have multiple volatile compounds, they will each exert their own vapor pressures that you actually have to add together to find your total vapor pressure. Okay, if you want to see an example of this, last Wednesday, number 5 was an example, and also tonight's challenge problems has a really good volatile vapor pressure lowering problem. It was pretty much one of the hardest ones I could think of them ever giving you. I think if you could do tonight's, you can do the one on the exam. Kind of the other, one other thing about this is when you have volatile solutes or compounds, you may see deviations from Raoult's law due to interactions between these volatile compounds. I would expect to more see that potentially in a multiple choice theory question. Again, I wouldn't really expect them to ask about deviations on a long answer exam. And then kind of the other point I want to bring up is about osmotic pressure, and it's what reverse osmosis is. Okay, and reverse osmosis is if an external force is applied onto the system and that force is greater, or sorry, if that pressure of the external force is greater than your osmotic pressure, then reverse osmosis will occur. Okay, so if your external force or external pressure is greater than the osmotic pressure, reverse osmosis will occur, which causes purification, right? Solvent will flow from highly concentrated solutions to lower concentrated solutions, or instead of a lower concentrated solution, it may flow to pure solvent, right? That would kind of be the purification. Okay, so again, I believe last Wednesday I gave an example of a reverse osmosis question that I absolutely love. I made it a multiple choice question. It easily could be made into a long answer question. And I definitely think that that's a possibility of something you could see on Friday. Not saying you will, but definitely if you haven't seen it, maybe go back and check out that problem. Okay, and so that's really all I have. Really the last note before I start taking questions is just realize that I went over some of the main points, but there are definitely other points that are important, both for a long answer exam, but especially for later on when you get to the multiple choice section of chapter 11, right? I didn't go over ion pairing, which is how we see deviations from the Van't Hoff factor. Definitely know your solution terminology. You'll see that in tonight's challenge problems, right? Hypo versus hyper versus isotonic solutions. Yeah, I don't know. That's really the only comments I wanted to make. Without further ado, this is your guys' turn. If there are any questions on any of this material, I'm happy to answer them. And
I have a question about the Van't Hoff factor.
Yep.
So the Van't Hoff factor applies to the solute, right? Like if it's being dissolved in something?
Yeah. I don't think I can ever think of an instance where a solvent would dissociate.
Okay, and then just a follow-up question to that. So there's like a problem on the homework that's asking to find like the molecular weight when something is being boiled. And if it's like unknown, how are you supposed to find the Van't Hoff factor for that?
So I'm trying to think this through my head. So you're trying to find the Van't Hoff. Do they give you like a general formula or anything?
Well, they say like it's 12.91 grams of the compound dissolved in 244.2 grams of ethanol, and then it tells you like you can figure out the delta T.
Mm-hmm.
And then they give you the KB.
Do you have the problem in front of you?
Yeah, I do.
Do you mind reading it for me?
Sure. The boiling point of ethanol is 78.5 degrees Celsius at 1 atmosphere. KB of ethanol is 1.22 degrees Celsius per molar. In a laboratory experiment, students synthesized a new compound and found that 12.91 grams of the compound were dissolved in 244.2 grams of ethanol. The solution began to boil at 78.737 degrees Celsius. The compound was also found to be a non-volatile and a non-electrolyte. What is the molecular weight they determined for this compound?
Perfect. Thank you so much. So that's actually a great question to ask. So notice how they said the solute is non-volatile. Okay, if they say that, and you're doing a vapor pressure problem, remember that just means that that will not create a vapor pressure. Now, if it says it's a non-electrolyte, which they often will in problems, if it says it's a non-electrolyte, your Van't Hoff factor is 1 automatically. Okay? So
Okay.
be wary of language like that. So if in the problem they say it's a non-electrolyte, it does not ionize, it does not dissociate, those are all ways to tell you that your Van't Hoff factor is 1. Okay?
Okay, so non-electrolyte doesn't mean non-volatile. They're like different things.
They're different. Volatile just means will it create a like vapor pressure, and electrolyte is will it split into ions or not. Correct. They're different.
Okay, perfect. Thank you
Yeah.
so
So
much.
for that problem that you actually said, I'm not sure that they needed to tell you it was non-volatile, but the fact that they said it was non-electrolyte is extremely important. And if they didn't tell you that, they would have had to show you a formula or something.
Okay, that
Okay.
makes sense. Thank
Yeah.
you.
If you ever think you don't have enough information about the Van't Hoff factor, look for factors like that. Because, yeah, they definitely need to indicate that to you unless you're solving for it. So, great question. Are there any other questions?
So if you're looking at a compound and like you're trying to decide if it's non-volatile or volatile, like how can you tell by just like looking at its like chemical equation or something? Like I get that it has to exert like a vapor pressure, but like how can you tell that?
It's a good question. Definitely for our purposes, I mean, even for me, that would go over my head. They would 100% tell you if it was volatile or not. And we'll kind of leave it there. I would say, yeah, no, they would definitely tell you if something was volatile. And if they don't say it's volatile, I would assume it's non-volatile. Okay, so in my problems, if we add a solid solute and it's a vapor pressure problem, that solid solute is, I either say it's non-volatile or I am meant for it to be non-volatile. If you have multiple liquids mixed together, again, they should probably talk about that, but like they should probably specifically say that it's volatile. But yeah, you'll typically see it be volatile if there are multiple liquids. So last Wednesday, my example was water and I don't even know what the other compound was. I don't know, ethanol maybe, water and ethanol, right? So 2 liquids, and I mentioned that they were volatile. Tonight, challenge problem number 6. I actually give you a solution with 3 different liquids in it. I tell you they're all volatile, and then I say to this solution, you add glucose, a non-volatile compound, to it, and go from there. Does
So
that
for
make
the
sense?
differences, yeah, it does. So like if something is volatile, that means it will have the vapor pressure.
Mm-hmm.
You were saying it would be added vapor pressure, so then you just change the equation to be like deviated from the blanking on the name, but the equation that you
Routes
use
law.
for it.
So you can have multiple volatile compounds and they don't deviate from routes. Okay. You see deviations from routes is way more complex than we would ever see. You might just see it on a theory question on a multiple choice exam. But when you're doing calculations, so again, the example from last Wednesday or the one I'm giving tonight, you're assuming that it follows Raoult's law. It's just an adjusted Raoult's law, right? So if you have, I'm going to use last Wednesday's problem as an example. We had water and ethanol. Each one of those is volatile and creates a vapor pressure, which means our total vapor pressure is equal to the pressure of water plus the pressure of ethanol. Okay? But based on Raoult's law, the pressure of water is equal to the mole fraction of water times the vapor pressure of pure water. And the pressure of ethanol is, based on Raoult's law, equal to the mole fraction of ethanol times its pure vapor pressure. Okay, so it's still Raoult's law. It's just Raoult's law including multiple compounds. that make a little more sense?
Yeah, it does. Thank you.
Okay. Yeah, we don't have the skills to calculate deviations from Raoult's law. So even if we have multiple volatile compounds, we're going to assume that they stick to Raoult's law still. Okay, I'm going to take questions from the chat because there's 2 in there. And then if there are more questions, people can type them or unmute. So Gabby asked, would Van't Hoff factor only work with ionic compounds? So this, I think, kind of goes into Kayla's question as well. So if you have a compound that is covalently linked, right, so it's not an ionic compound, you do have a Van't Hoff factor, but it's 1, okay? So it doesn't affect your calculations. So you always have a Van't Hoff factor, but if it's a covalently linked compound, it's going to be 1. And if it's an ionic compound, meaning it has metals and nonmetals, it will have a Van't Hoff factor that is greater than 1, right? And that kind of feeds into Kayla's question. Is there an easy way to tell if a compound is an electrolyte or non-electrolyte? If it's an ionic compound, so if it's made of metals and nonmetals, it's going to be an electrolyte for our purposes. And if it's covalently linked, it's going to be a non-electrolyte, okay? So really, it's just analyzing, is it ionic or covalently linked? And remembering that ionic compounds need to have a metal cation portion, while covalent compounds are only going to contain nonmetals. Okay. Any remaining questions?
I have another question about the homework.
Okay.
So there was a question asking to convert from like percent by mass to the mole fraction.
Mhm.
So generally, how would you do that? And they give you the density too.
Mole fraction. So don't know if you have mass percent. I think the density is just distracting information. So I'd assume that there's 100 grams. And so you can just drop the percentage sign. So let's say you have 30% solute, whatever that is, 70% solvent. If you assume you have 100 grams of solution, you can drop those percentage signs and say, I have 30 grams of solute, 70 grams of solvent. I would use their molar masses to convert to moles of each, and then you can find your mole fraction.
But then if you don't know what the solution is, then you would use the density. Because they just say it's like an aqueous solution with like blank percent of mass in it.
They don't tell you what the solute is?
They tell you that it's the solute is ethanol.
So that's why. So ethanol, you need to know the formula for that, which on an exam, you guys would be given the formula for that. But if it's an aqueous solution, it means the solvent is water. And so, yeah, I'm trying to think if you would need the density. I don't think you need the density of that. Unless if they tell you you have, 5 liters of solution. But yeah, I don't think you need density. As long as you know that the solute is ethanol, if it's an aqueous solution, that means its solvent is water. And so from there, you would probably be able to solve that.
Okay, thank you.
Yeah. That's why homework as a general basis is pretty good, but they definitely word things and have you do things that are a little deviant from how your professors would ever have you do it on the exam. I remember like book problems, they sometimes would ask the most ridiculous questions. Any remaining questions? Oh,
I also have, I just want to quickly go back to like the volatile versus non-volatile and just make something clear. So if you have like you were saying in your, in Wednesday's session, you had volatile, you had like 2 volatile compounds. And so if you're trying to find the total vapor pressure for that, you would, and say you had 2 compounds, basically what you would do is the mole fraction of one of the compounds times the vapor pressure of that plus the mole fraction of the other times vapor pressure to get the total. Is that what you would do?
absolutely. Yeah,
Okay.
definitely check out tonight's problem because I think that'll help reinforce it. But
Mhm.
basically, right, let me go back. Right, Raoult's law, P's solution here. I know it says solution. This is kind of assuming that there's only one volatile portion, right? It should probably say P of solvent in solution, right? And so you would do this separately for both volatile compounds, right? So water and ethanol, it would be the pressure of our water in our solution is equal to the mole fraction of water times the pure vapor pressure of water. And basically, the P of water here on the left-hand side is basically your partial pressure of water, okay? And so if you have another volatile compound that has a vapor pressure, you would use Raoult's law, but for using its mole fraction and its pressure to find, so we would find it for the partial pressure of water, we'd use it for the partial pressure of ethanol, and then just like we did back in chapter 5 last semester, to find the total pressure, you just add together your partial pressures.
Okay, that cleared it up. Thank you.
Yep, and whatever lecture video it is, I know Dr. S goes through an example and it writes out kind of the extended Raoult's law when you have multiple volatile compounds. And again, also the solution video tonight. Again, it's number 6. You'll see how I did it there. Okay, if there are more questions, I'm definitely happy to answer them. I'm just gonna slowly, in case people have to go through the 6 challenge problems. So the first is multiple choice, just because I liked the problem and didn't really know how to make it a long answer. And then the other 6 problems are all long answer. Okay, but again, if there are any questions, I'm happy to answer, whether people want to unmute their microphones or text it in the chat.
So is non-volatile and volatile solution just like another way of saying like non-ideal versus ideal solutions? Like, is it like interchangeable?
So my interpretation of the lecture was that as far as we're concerned, if there's only one volatile component, right, so there's only the solvent is the only thing creating a vapor pressure, I think we assume that that's automatically ideal, okay? But when we start adding multiple volatile compounds, right, and they each have their own vapor pressure and they're each chemically unique, right, then we assume that they follow Raoult's law, right? How I solve number 6 is assuming that the solvents are ideal and follow Raoult's law, okay? But in actuality, when you have multiple volatile compounds, you can see deviations from Raoult's law, okay? And those are non-ideal. Non-ideal is when you have multiple volatile compounds and they deviate from what you'd expect Raoult's law to say the pressure is, okay? So when we'll see ideal solutions when there's one or multiple volatile compounds, I guess. That's what I'm trying to say. Does that kind of make sense?
Yeah, thank you.
Yeah. So again, if there's only one volatile compound, it's automatically ideal. If there's multiple volatile compounds, for our calculations, we're going to assume that they're ideal, which just means they follow Raoult's law. But if you actually look at it in real life and record data in lab, you will find that you might actually see deviations from the calculated pressure. And those are just non-ideal solutions. Okay, so here's number 4 and 5. I really like number 5. Actually, I kind of like all of these, but number 5 I think is a really good one. I think it puts a twist on a classic problem. Okay, just gonna switch in through like 5 seconds in case people want to take a photo of it. If not, again, it will be posted shortly, or I can go back to it after, of course, too. Okay, I just want to get to the last two problems. So number 6, again, this is one where we have 3 different solvents that I say are all volatile compounds, because I say we mix them, and I say into this solution, glucose is added, a non-volatile solute, right? And so I think if you have a volatile compound, I think they will be very explicit and say that. Also, if something's volatile, they need to tell you the pure vapor pressure, unless that's something you're solving for, which actually would have been a really good problem concept. But the one thing I want to comment on, in case you look at my solutions and you're unsure, I do say it multiple times in the video, but isopropanol is sometimes denoted as IPA. Okay, so if you're looking at the solutions and you're saying, what is IPA? It's just isopropanol. I apologize. I shorthand in lab write IPA all the time for isopropanol. And then 7, I would definitely star and definitely try on your own. That is something, and I say this in the video where I review these answers, a problem like 7, or at least the trick behind number 7, where there are multiple solutes. This is something that I believe has been on the exam in the last 3 years, maybe 4 years. Maybe I had it. I don't even know. I'm too old at this point. But it's been around, a type of problem like number 7, where it's your classic boiling or freezing point problem, but there's multiple solutes. That has occurred many times. Okay, and if it's somehow a problem like number 7 came up for osmotic pressure type problem, kind of the thinking and reasoning that I use in number 7, I would apply to osmotic pressure as well. Yeah, I don't know if I've ever seen that. Okay, and you'll kind of see, I'm trying not to give away the trick. Okay, so I'm gonna stop sharing and end the recording now, but again, if there are any questions, I'm happy to stay around, answer, and I'm happy to come back into this PowerPoint if needed.